So here we are. So we were at this position dealing with double integrals over non-rectangular regions. And we had this, well, first of all, you have to be careful in setting up the limits for these integrals, okay? So if you look back to this example 1.2 in the notes, we were integrating this given function f, which is 4x cubed plus 4y cubed, integrating it over this region R in the plane there. You can see this is patently a non-rectangular region. And so setting up the limits for these integrals you have to do kind of carefully. So we explained that you work from the outside in. So the decision first is you look at the y integral, which is the outer integral as it's written down here. The y integral is the outer one. So you decide on the limits for the y variable as the limits you need to move between in order to capture the region. So clearly we have to take in all values of y between 1 and 4 because there are parts of the surface there, sorry, parts of the region there at all y values from 1 to 4. And then you pass to the inner integral, which is the x integral. Now, because the outer integral is the y integral, the outer integral kind of provides a y value to the inner integral. And it provides a y value somewhere between 1 and 4. You can kind of think of the outer y integral like a for loop in a programming sense. So the outer y integral is like an outer for loop. It sets up and provides a y variable to the inner integral, to the inner x loop, if you like. So the inner integral is taking a given value of y, and that given value of y will refer to one of these little horizontal strips across the region, the horizontal strip located at that value of y. So y, this y appearing in the integrand here, you think of that as this y level of this horizontal strip. So for the purposes of this integral, of course, that y value is fixed. For any run through the inner for loop, the variable of the outer for loop has some fixed value. And so the question is then, what limits do you move between for the x variable, for the inner integral? Well, at that value of y, you only need to move from, well, you need to go all the way up to x equals 2, but you only have to begin at the horizontal x coordinate of that leftmost point on that strip. So that's this point down here, but what point exactly is it? Well, this strip is ending on this curve, and the curve has the description y is equal to x squared. So that means if the strip is at height y, means the x coordinate there underneath the left end of the strip must be the square root of y. So that's why you're only integrating from the square root of y up to 2. So for low values of y, for y near 1, you know, those strips are quite wide because the square root of y is going to be close to 1. But as y gets very high, so it gets very close to its upper limit of 4, its square root will be getting very close to 2. So that's why, you know, so the strips narrow down, as you can see, as you get higher up in the diagram. So this inner integral is going between a much shorter interval for the higher up values of y. So that's how you set up the limits. Now to evaluate it, and this is where the kind of metaphor with the programming kind of breaks down a bit, to evaluate it, you evaluate it from the inside out. Because the outer integral kind of can't take place until it knows the value of the inner integral, so to speak. So maybe the programming analogy kind of breaks down, but you perform the inner integral first. And the inner integral can be performed by just keeping y as this symbolic constant. Just as we do when you're differentiating with respect to x, you treat any other variables as just like they're just placeholder constants. Do the same for integration. Okay, so we worked through that example last day. I won't work through the details of it again. You perform the inner integral, and that means if you've done it correctly, then there won't be any x's left because you'll have integrated out any dependence on x, and you'll just be left with the expression which corresponds to general horizontal strip at level y. So you end up with this expression which depends on y. And you then integrate that between the limits for the y variable between 1 and 4 here. And you get the overall value of the integral, okay? Which, remember, corresponds geometrically what this integral is. It's the volume lying over this region and bounded by this region on the bottom and by the surface z equals fxy on the top or on the bottom. If the z values are negative, of course, the surface is lying underneath the plane, negative z values, but if z is positive, it's lying above the value, lying above the xy plane. Okay, so let's look at another example. So here we'll consider the function f of xy equals x squared. Oops. And we want to integrate f over the region R and this is the region R in the first quadrant of the plane. We'll draw a diagram of it now in a moment. And the boundaries of this region are bounded by the hyperbola xy equals 16. So that's a curve in the plane. So bounded by that hyperbola and the two axes, x equals 0 and y equals 0. And the line x equals 8. So let's draw a picture of what's going on here. So we got the y-axis, we got the x-axis, so we got the x equals 0 line, the y equals 0 line. We got the line x equals 8, so 8 will be up here somewhere. There's the vertical line, x equals 8. Now, x times y equals 16. Well, one point that will go through is the point with coordinates 8, 2. When you have x equals 8 and y equals 2, then you've got a product of 16. Just give us another. Oh, I need another line here. So I need 4, 1, 2, 3, 4. Yeah, and I need another line. And the line x, we'll say the lines x equals 8 and x equals y. So we're going to deal with the 45-degree line as well. And so there's a point on the 45-degree line, which is the point with coordinates 4, 4, and that's also on the hyperbola. So the hyperbola is this kind of curve here, which is kind of, and for very high values of x, x gets very small, and for very high values of y, x gets very small in order to always maintain the product xy as being 16. And so the region we're integrating over here is this region traced out in red here. Okay, so that's this is the region R, the region that we want to integrate over. Okay, so this is obviously not a rectangle. It's got it's got 4 sides. 3 of the sides are straight. 1 of the sides is curved. But they're, and this one, we got a right angle over here, but we don't over here. So it's certainly not a rectangle. Okay, so we want the integral. We want the integral to be the double integral over R of x squared dA. So in other words, the double integral over R of x squared dx dy. So what we start to space it out now as a repeated integral or a pair of nested integrals. So we've got y as the outer integral. So what values does y have to go between in order to capture the image? Well, y has to begin at 0 and go all the way up as far as 4. Okay. So that's fine. Y goes from 0 all the way up to 4. So then that outer integral is like an outer for loop in programming. It's providing a value of y to the inner integral. So a value of y refers to some value between 0 and 4. And then the x integral wants to take us across one of these horizontal strips across the surface, across the region. But now we run into a slight problem here. The starting point, the left starting point of these horizontal strips is okay. The horizontal strips always begin on this line. So they always start at y. For a given y value, the x coordinate here is also y, because this is the line x equals y. And for low values of y, these horizontal strips all go up to the value 8. But for high values of y, they don't go all the way up to 8. They end on this curve. So there's a kind of a, we can't have a unique description of this upper limit, because sometimes it's 8 and sometimes it's whatever the x coordinate of the point on this curve is. Okay, so we can't put a nice, simple, tidy expression there in that upper limit. So that's a problem. So you kind of get stuck. The way to resolve it is to split into two subintegrals. There's an obvious way to, there's a sensible way to split the region up. To split it up at that dividing point between the two types of description that you want to give to the upper, that you want to give to the upper limit for x. So we'll think of this region now as R1 and R2. So we can now say that we'll think of this as the integral over R1 of x squared dA plus the integral over R2 of x squared dA. Okay, and just as you can split one-dimensional integrals along a line, just as you can split those up using an intermediary point, or integrals along a curve in the plane, you can split those up using a middle point along the curve. Well, here's a kind of similar thing. You've got some overall two-dimensional region to integrate over. You're allowed to split it up as the integral over one part of the region plus the integral over the other part. As long as the regions R1 and R2 are a partition of R, meaning that they completely cover R and they've got no intersection. Okay? Obviously, if R1 and R2 intersected a bit, then you'd be counting that contribution twice, because it would contribute to this integral and to that integral. So as long as the two areas have no intersection, except along their boundary, and that they cover the whole of the original region, you're fine. So now we should be able to decide on these limits. And we've more or less specified it in our original discussion. So now this first integral is only going from y from 0 to 2. The second one takes you from 2 to 4. In the first integral, the horizontal x strips all begin at y and they all end at 8. But for R2, they're still beginning at y, but now they're ending at the point on this curve. And the points on those curves have x coordinate 16 over y. So this upper limit of integration there is 16 over y. Okay. So doing that splitting has allowed us to get it into a form which we can now evaluate. Okay. Okay. And so I mean, that's the kind of hard work done, or that's the kind of mathematical work done. Then, okay, each time it just integrates to x cubed over 3. You've got these limits, a limit y and 8 dy. You've got x cubed over 3. And you've got a limit y and 16 over y dy. So, crikey, you get 8 cubed, whatever that is. 8 cubed minus y cubed over 3. So 2 to 4. Integral from 2 to 4 of 16 cubed over 3y cubed minus y cubed over 3. Okay, but there's now it's just a plain old one-dimensional integral, which, you know, shouldn't present you any bother. Okay, so if you forgive me, I won't carry that out, but it's just an integral of polynomial terms in y. You've got some negative powers, so, well, what the hell? So you get 8 cubed y minus y4 over 4. That's all divided by 3. You go 0 and 2. And then you'll have, so this is y to the minus 3. So it's going to have to go up to y to the minus 2. So it's going to be 16 cubed over 3y squared. But there's going to have to be a compensatory minus 2. So you're going to have to have a factor of minus 2 down there. Aren't you, I think? Yep. And then you've got a minus y to the power of 4 over 12. Evaluated at 2 and 4. You're adding those two together. Okay. No, I'm not going to take that any further. But, you know, you could work out what it is or get the computer to tell you what it is. So that's a basic principle. We can also do the integral the other way around. The integral is in the opposite order. So we might also integrate over r x squared dy dx. So we now put x as the outer integral and y as the inner integral. Try and get my diagram back. You can see you're going to run into similar problems here. The x integral is easy to say. You just integrate from 0 to 8. And these y integrals, they always begin at y equals 0, because now you're thinking of splitting it up into vertical strips. You're talking about a vertical strip at a position x between 0 and 8. These vertical strips all begin at the bottom at y equals 0, but sometimes they're ending on this straight line x equals y, and sometimes they're ending on the curve, on the hyperbola xy equals 16. So again, you're stuck here if you're trying to render it as a single double integral. So you just simply split it apart in the same way. So you'd integrate first x from 0 to 4, and then y will go from 0 up to x. And then the second half would go from 4 up to 8. And then y would be going from 0 up to 16 over x. Okay, so this will bring you to, after evaluation, to the same value as before. the same value that you had up here. Okay, if you actually evaluate all of that, it will come out as the same answer here. Okay. So you just have to be careful with non-rectangular regions. You just treat them carefully, and especially when you're flipping the order, the descriptions of them look quite different. They may split up in different ways, and the limits of integration will look different. Okay, because you're looking at the region in two different ways. In one way, you're splitting it up into strips parallel to the x-axis, and the other way, you're splitting it up into strips parallel to the y-axis. Okay, so there's two ways of looking at the integral, or performing the integral, lead to different descriptions for the limits. So, okay, any questions or queries on that? Okay. Okay, we also want to talk about another thing we need to do with double integrals, and that's to completely change the coordinate system that we're using. And we normally like to think in terms of the Cartesian coordinate system, x and y, because, well, kind of makes sense. It's a nice way to describe a plane and points in the plane, but it isn't always the most sensible way to describe points in a plane. There are plenty of other, well, there are a number of other coordinate systems which also describe points in the plane equally well. So this point here might have coordinates a, b. So you go a steps along the x-axis, b steps along the y-axis, but equally well, you might want to describe it as using polar coordinates, r theta, and they describe the location of the point while saying it's r units away from the origin in that direction, or that direction. So they name a direction using an angle, theta, and they specify how far you have to go in that direction. It's just as good a way of referring to the location of the point A as giving its A and B coordinates. There's nothing to choose between them. They're both equally good, equally valid. What leads you to use one or the other is what you're using them for, what the context is. And if things are kind of rectangular and boxy and kind of aligned with the x and y axes, then it's probably easiest to use the Cartesian system. But if things are kind of circular or kind of got some kind of rotational aspect to them, then probably polar coordinates would be the suitable or appropriate coordinate description to use. So the question is, what does that mean for integrals? So what we're describing here is, in the one-dimensional case, when you had an integral of f of x with respect to x, we knew we could always make a substitution. Or in a way, it's kind of like the chain rule. That you could substitute x with an equivalent expression in terms of another variable t. So you then want to make t be the variable of integration, or t be the variable that you're talking about. So you can replace the expression f of x with whatever its equivalent expression in t is, but you don't just integrate that with respect to t. There's an adjustment to make to the differential. You need this extra factor dx over dt multiplied by the new differential dt. Okay. So you have this compensatory factor, if you like, this derivative dx dt, which is a new factor for the integrand. Okay, a new factor multiplying the equivalent expression in f in t, and then you integrate the whole thing, and then that gives you the same answer. Okay, so this factor of the derivative here, this dx dt, that accounts for the different way that the variables x and t will measure length. Now, in 2 dimensions, there's a difference in the way that different coordinate systems measure area. Okay. And this difference is picked up by this object here, which you'll recall we met a while ago. This is the Jacobian determinant. of the transformation from one set of variables to the other one. It was all the way back in the partial derivatives chapter. Back here somewhere. It's just before this, wasn't it? Jacobians of the transformation. So this object here in equation 102, the Jacobian of a transformation from a coordinate system xy to a new coordinate system xt, there is a Jacobian determinant associated to that, which is the determinant of this 2x2 matrix of all the partial derivatives. So you got dx ds and dx dt along the first row, and dy ds and dy dt along the second row. Okay, so you take the determinant of that. And that, the Jacobian determinant, kind of accounts for or measures the different ways that these coordinate systems measure area. So if I have my integral in terms of x and y, I want to produce the same integral in terms of the new pair of variables s and t. So I simply replace f with its equivalent expression in s and t, substitute in whatever x is in terms of s and t and y is in terms of s and t, and I have the two new differentials ds and dt, but I also need the Jacobian of the transformation as well. So let's look at this polar coordinates example here. Now the relationship between polar coordinates and Cartesian coordinates is given by these two equations. And when you look at the Jacobian determinant, it comes out to be r. Now we actually use the absolute value of the Jacobian determinant. So the absolute value of this is the absolute value of the determinant dx dr dx d theta. So we described this a few weeks ago. dy dr dy d theta. Okay, so there's a few steps, but we saw before that this quantity came out as r. There was, when you evaluate the determinant there was a cos squareds plus sine squareds of the same angle, so that gives you 1. So this Jacobian quantity comes out as r. So that means if you're doing an integral of something with respect to dx and dy, it's going to be equal to the same integral, the same double integral, but r dr d theta. So this r here is the absolute value of the Jacobian. Okay, so that comes in as a new factor. So here was your f of xy. Here would go the equivalent expression in terms of r and theta. Okay, so we'll just finish off. We'll just look at a quick example. So in this example, we're asked to integrate over this region R here, integrate this function 1 over x squared plus y squared. Now there's two reasons why the Cartesian coordinates is a bad system, or not a bad system. There's two reasons why the polar coordinates is a much better system for performing this integral. The first reason is that the region R is much more rotational. It's much more circular. It's much more suited to the polar coordinates. So it's defined in terms of circles. It's the region between the circle of radius A and the circle of radius B. But secondly, so the region is kind of circular looking. Secondly, the function you're integrating has quite a nice description in terms of polar coordinates, because that quantity x squared plus y squared is exactly the square of the radius. X squared plus y squared is equal to r squared. So both the integrand, the function you're integrating, and the region, they are both highly circular or highly suitable for polar coordinates. So we would expect that the integral would be a lot easier to carry out in polar coordinates. So this is how it transforms. You're integrating 1 over x squared plus y squared dx dy over this region. So you replace 1 over x squared plus y squared with 1 over r squared, and the two differentials dx dy get replaced by r dr d theta. Okay, so you got the Jacobian and then the product of the two differentials dr and d theta. So the integrand simplifies a little bit. It's now just 1 over r. And then you think about deciding on the limits of integration. So the outer integral is now the theta integral. So you ask, what value of thetas do you have to integrate between in order to capture the region? Now that shaded region there, you can see you've got parts of the region at all angles from theta equals 0 all the way up to theta equals pi over 2. Yeah? You have to look in all those directions in order to see the whole of the region. From theta equals 0 to theta equals pi over 2. So that gives you values for the limits of theta. So then you look at limits for the values of r. Well, for a given value of theta, for a given angle theta, between what values of the radius do you have to move between in order to capture the region r? Well, the region r lies between these two circles. So you have to go from r equals a out to r equals b. Okay? So that's why the limits on the r integral are a and b there. So actually, in a funny kind of way, you can say that this region R is a rectangular region in polar coordinates. In polar coordinates, it just has 4 constant fixed limits. 0 and pi over 2 for the angle theta, and a and b, whatever they are, for the radius. So in polar coordinates, this region, although it's not what we normally call a rectangle, but in polar coordinates, it's acting like a rectangle. It's a region with constant limits at both sides for both of the variables, for r and theta. Okay. So that kind of backs us up or supports the case that it was a good idea to translate into polar coordinates for this. And then actually carrying out the integral, well, I've written ... in the notes. There's just a couple of things to do. You integrate 1 over r. It gives you the logarithm of r. You evaluate that at b and a, so you got the logarithm of b minus the logarithm of a, or that's the same as the logarithm of the ratio b over a. Okay, so the logarithm of a difference is the same as the logarithm of the quotient. Sorry, the difference of logarithms is the same as the logarithm of the ratio. So the r integral comes to the logarithm of b over a, and then you're just integrating it with respect to theta from 0 to pi over 2. So that just multiplies it by pi over 2. Okay. So the integration actually is relatively painless after you've done the translation to the correct coordinate system. Okay, I better finish there. We've gone over a couple of minutes. But that sets you up for, there's plenty of exercises there on rectangular regions, non-rectangular regions, and changing coordinate systems as well. We might say a little bit more about this next week before we do the final section.